The interstellar traveller 3i Atlas just did something no one predicted. It suddenly brightened and turned bluer than the sun itself, and scientists can't explain it. Hit like and subscribe to stay updated. We begin our story with a date, October 29th, 2025. On this day, deep in space, something incredible happened. An object, a visitor from another star system, was passing by our sun. This traveller was named 3i Atlas. It was on a long journey through our solar system, a place it had never been before. We were watching it, of course. Our space telescopes track these visitors, learning what we can from these rare guests. But no one was prepared for what 3i Atlas was about to do. As it moved past the sun, hidden from our view here on Earth, it changed. It suddenly became much, much brighter. This wasn't a small change. It was a huge, impossible explosion of light. At the same time, it began to glow with a strange new colour. It turned bluer than our own sun. This was a deep, noticeable blue that shocked the scientist watching the data. Our sun is a brilliant yellow-white. To see something become bluer than that, right next to it, was deeply strange. It was like seeing a piece of charcoal suddenly start glowing brighter and bluer than a welding torch. It simply shouldn't happen according to the rules we know. This wasn't just a guess or a blurry image from a single telescope. This amazing event was confirmed by a team of our best eyes in the sky. Spacecraft like Stereo, an observatory designed to watch the sun, saw it happen. SOHO, a long-serving and reliable space telescope, also recorded the change, and even a weather satellite named GO, which watches the sun for solar flares, saw the same thing. 3 different sets of instruments, in 3 different places, all told the same unbelievable story. 3i Atlas had put on a light show that broke all the rules. When multiple independent witnesses all say they saw the same impossible thing, you have to start taking it very seriously. The scientific community was stunned. The people who spend their entire lives studying comets and asteroids were left scratching their heads. Even the top scientists in the field, the ones who write the textbooks, had to admit something profound. They had no idea why this happened. In science, that is a very big deal. It's rare for a new observation to completely stump the experts. Usually they have a few good ideas, a few theories to test. But for this event, the initial reaction was just pure surprise. The data didn't fit any of the usual explanations. It was a true, deep mystery, unfolding millions of miles away in the darkness of space. This admission of not knowing is not a failure. It is the very heart of scientific discovery. It's the moment when we realize the universe is more complex and more wonderful than we thought. It opens the door to new ideas, new possibilities that were once considered science fiction. The baffling behavior of 3i Atlas forced everyone to step back and ask fundamental questions about what these interstellar visitors really are. Are they just chunks of rock and ice, or can they be something more? Immediately, 2 main ideas began to form. These ideas are very different from each other. The first idea is that 3i Atlas is a natural object, but a very, very strange one. Some scientists think it could be a special kind of comet, a superactive comet. This means it might be made of materials we don't often see. It could be packed with frozen gases that are extremely explosive when they get warm. When 3i Atlas got close to the sun, the heat could have set off a chain reaction, causing it to erupt with incredible force and light. It would be a comet, yes, but a comet unlike any we have ever seen in our own solar system, a true alien comet. The other idea is much more radical. It's an idea that many scientists are hesitant to even say out loud, but one that the strange evidence forces them to consider. Some wonder if 3i Atlas is not a natural object at all. Could it be a piece of alien technology? Perhaps it was a probe or a piece of a larger craft, dormant and quiet as it travelled through the cold of interstellar space. Then, as it passed our sun, the sun's intense energy might have acted like a switch. It could have woken up the object, causing its systems to power on and glow with a brilliant blue light. This is an extraordinary claim, and it requires extraordinary evidence. But the behaviour of 3i Atlas was so extraordinary that for some, this idea has to be kept on the table. This is not just a story about something that happened in the past. It's a story about something that is happening right now. The mystery is still unfolding. 3i Atlas is now moving away from the sun and is heading back out into a part of space where we can see it again. A very important date is coming up. On December 19th, this strange object will be visible from Earth once more. Our biggest and best telescopes on the ground and in orbit will be pointed right at it. They will be waiting to see what it does next. Will it still be glowing? Will it have changed? We need to be ready. We need to be watching. The answers to this incredible cosmic puzzle might be just around the corner, waiting for us to find them. The world will be watching to see if 3i Atlas reveals its secrets. The countdown has begun. Now we must explore the most shocking part of this story in more detail. Let's talk about the impossible brightness of 3i Atlas. This wasn't just a little flicker. It was an event so extreme that it challenges our basic understanding of how things work in space. This is the heart of the mystery, the central clue that tells us something profound is going on with this interstellar visitor. We are now entering the part of the story called the Sun-Eating Light Show, impossible brightness. To understand how strange this was, we first need to understand how normal comets behave. Think of a typical comet from our own solar system. As it gets closer to the sun's heat warms it up. The ice on the comet's surface begins to turn into gas. This gas shoots out, creating a glowing cloud and a tail. This process makes the comet get brighter. You can think of it like a car slowly speeding up on a highway. It starts off dim when it's far away, and as it gets closer to the sun, its brightness smoothly and predictably increases. Scientists have studied this for centuries. They have mathematical rules that describe this process very well. It's a gradual, understandable change. But 3i Atlas was not like that at all. It didn't follow the rules, it didn't gradually speed up. What 3i Atlas did was like a car that was cruising along at 50 miles per hour, and then, in the blink of an eye, jumped to 500 miles per hour. Its brightness didn't just increase, it exploded. The change was incredibly fast and incredibly steep. It went from being a relatively dim and uninteresting object to one of the brightest things our solar telescopes could see near the sun. This sudden jump is what scientists call an outburst, but the scale of this was far beyond a typical outburst. It was a sustained, roaring fire of light. To put a number on it, scientists use a measurement called a brightening rate. For most comets, this number is usually between -3 and -5. It's just a way of describing how quickly the brightness ramps up as the comet gets closer to the sun. The key thing to know is that a more negative number means a much, much faster brightening. A comet at -5 gets brighter much more quickly than a comet at -3. But the measurements for 3i Atlas were shocking. Its brightening rate was calculated to be -7.5. This number is almost unheard of. It's so far outside the normal range that it looks like a mistake in the data. A rate of -7.5 means that it got hundreds of times brighter, far more dramatically than any normal comet should. This incredible event happened at the worst possible time for us to see it from Earth. The brightening happened while 3i Atlas was hidden behind the sun from our point of view. It was in a part of the sky called the solar conjunction. This means our powerful telescopes on the ground, the ones on mountains in Chile or Hawaii, were completely blind to it. The sun's blinding glare would have totally washed it out. It was a secret light show performed on a stage where no one on Earth could directly watch. But luckily, we have eyes in space. Our solar telescopes are not on Earth. They are in orbit, and they are specifically designed to look at the sun and the area around it. They have special tools that can block out the sun's intense light, allowing them to see the faint things happening nearby. It was only because of these dedicated spacecraft that we saw this event at all. They were our only witnesses to the impossible brightening of 3i Atlas. Without them, this visitor would have passed by, and we would have never known its secret. When scientists look at data like this, they are very careful. They check and recheck their work. But the numbers kept telling the same story. The brightness of 3i Atlas was off the charts. So, in their early reports, you will see them use careful scientific language. They will say that the reason for this brightness is unclear. But we need to understand what this word really means in science. When a scientist says something is unclear, it doesn't just mean they are a little confused. It means that their best models, their most trusted theories, and all their computer simulations cannot explain what they are seeing. It is a code word for, this breaks our understanding of physics as we know it. It's a sign that we have stumbled upon something truly new. The full scientific report with all the details and analysis hasn't been published yet. It takes time for scientists to go through every piece of data and make sure their conclusions are solid. But the early information that has been shared is already making waves. The fact that multiple spacecraft, built and operated by different teams from around the world, all reported the same thing makes the evidence very powerful. It's not a glitch in one camera. It's not a mistake by one scientist. It is a confirmed event seen by a robotic fleet of observers. This makes the mystery of Three-Eye Atlas's impossible brightness very, very hard to ignore. It is a clue that points to something extraordinary happening to our interstellar guest. But what if this isn't just a weird comet? What if Three-Eye Atlas is something entirely different? Something engineered? The mystery of Three-Eye Atlas deepens when we look at its other strange quality. It wasn't just the brightness that was shocking, it was also the colour. As this object flared up, it began to glow with a light that was fundamentally different from the sun it was passing. This strange hue provides another powerful clue, another piece of the puzzle that points towards something truly exotic. Let's now focus on this aspect of the discovery in a chapter we can call Bluer Than the Sun, a cosmic chameleon. This visitor from another star didn't just get brighter, it transformed its very appearance. So not only did Three-Eye Atlas get super bright, but it also turned bluer than our own yellow-white sun. Let's think about what that means. The light from our sun is a mix of all the colours of the rainbow, but it peaks in the yellow-green part of the spectrum, which is why we see it as a brilliant yellow-white. Most objects in our solar system, like asteroids and comets, simply reflect this sunlight. A rock in space is like a grey wall in a yellow-lit room. The wall will look yellowish, because that's the colour of the light hitting it. A comet's dusty cloud usually just reflects sunlight, so it too should have a yellowish-white colour. But Three-Eye Atlas was different. It was like putting a blue light bulb in that yellow-lit room. The light coming from it had more blue in it than the sunlight that was hitting it. This wasn't a subtle change, not a slight blue tint that you could barely see. The measurements were clear. Across different instruments on different spacecraft, the data showed the same thing. The light from Three-Eye Atlas was measurably and significantly bluer than the direct light from the sun. The spacecraft have special filters that can measure the amount of red light and blue light coming from an object. When they compared the ratio of blue to red from Three-Eye Atlas, it had a much higher amount of blue than the sun itself. This was a direct physical measurement. It was an undeniable fact. The object was creating its own bluish light, and this glowing blue cloud around Three-Eye Atlas was not small, it was huge. The measurements indicated that the cloud of glowing material stretched out for 300,000 kilometers. That is a mind-boggling size. To put that in perspective, the Earth is about 12,000 kilometers wide. This means the blue cloud around Three-Eye Atlas was about 25 times the size of our entire planet. Imagine a glowing blue sphere in space, with 25 Earths fitting side by side inside it. This was not a tiny dot of light. It was a vast, shimmering cloud of blue, all powered by a much smaller object hidden in its centre. This sheer size and colour lead to a very important conclusion. It suggests the object wasn't just reflecting sunlight. If it were just a cloud of dust reflecting the sun, it would be yellowish-white and likely much fainter. The fact that it was so bright and so blue means something else was happening. The object was actually glowing. It was emitting its own light. This is a process called emission. Think about the difference between the moon and a star. The moon is bright because it reflects sunlight. A star is bright because it generates its own light through nuclear fusion. Three-Eye Atlas was behaving more like a star or a neon sign than a simple piece of rock or ice. It was actively producing this blue light. The source of this blue light is one of the biggest questions scientists are now asking. The specific colour of light that an object gives off is like a fingerprint. It can tell you what the object is made of and what processes are happening there. This blue light points to very unusual chemical reactions or materials that we don't normally see in comets from our solar system. Certain gases, when they are energized, can glow with specific colours. For example, the green glow of some comets is caused by certain carbon molecules. But a strong dominant blue glow across such a vast area is something new. It hints that the chemical makeup of this interstellar visitor is fundamentally different from the comets we're used to. What could create such a light? There are a few possibilities. It could be a very rare type of gas that was released from the object and then energized by the sun's radiation, causing it to glow blue. Or it could be a process involving plasma, a state of matter, where atoms are broken apart into charged particles. The interaction between this plasma and the sun's powerful magnetic fields could create a brilliant blue light. Another idea is that the dust coming off the comet was not normal dust. Perhaps it was made of extremely fine particles that are very good at scattering blue light, much more so than typical comet dust. Whatever the cause, the blue colour is a critical piece of evidence. It tells us that 3i Atlas is not just a passive reflector of light, it is an active, dynamic object that is generating its own spectacular glow. It's a cosmic chameleon that changed its colour in the heart of our solar system. This transformation, combined with its impossible brightness, paints a picture of an object that is truly alien. It forces us to wonder what it's made of, where it came from, and what powerful process was unlocked as it flew past our sun. The blue glow is a message, written in a language of light that we're only now beginning to try and understand. To see something so strange, happening in a place we couldn't observe from Earth, required a special set of circumstances. It required a team of robotic explorers, perfectly positioned in space to witness the unseen. These spacecraft are the unsung heroes of this story. They are our eyes in the sky, constantly watching the sun and its surroundings. Understanding how they work and what they saw is key to understanding the mystery of 3i Atlas. Let's now meet these amazing machines and see how our spacecraft saw the unseen. 3 main spacecraft were the key witnesses to this cosmic event. They were Stereo A, SOHO's LASCO C3, and GO-19's CCR-1. Each one is a marvel of engineering, and each one provided a unique piece of the puzzle. First, there's Stereo A. The name Stereo stands for Solar Terrestrial Relations Observatory. Its job is to watch the sun from a different angle than we do on Earth, giving us a 3D view of solar storms. It was in the perfect spot to see 3i Atlas flare up. Then there is SOHO, the Solar and Heliospheric Observatory. SOHO is a true veteran of space exploration. It has been watching the sun for decades and is one of our most reliable tools. Its instrument, called LASCO C3, is famous for discovering thousands of comets that get too close to the sun. So, for LASCO C3, watching an object near the sun is its specialty. It provided some of the clearest data on the object's sudden brightening. Finally, there was a more unexpected witness. GO-19. This is a geostationary weather satellite. Its main job is to watch Earth's weather patterns. But it also carries a special instrument called a coronagraph, the CCR-1, which looks at the sun's outer atmosphere to help with space weather forecasting. It was this instrument on a weather satellite that gave us some of the best information about the colour and the huge size of the blue cloud. These spacecraft can see things near the sun because they use a special tool called a coronagraph. Understanding a coronagraph is easy if you think about what you do on a sunny day. If you want to see something faint in the sky near the bright sun, you hold up your hand to block the sun's glare. A coronagraph does the exact same thing. It has a small solid disc inside the telescope that physically blocks the direct blinding light from the sun's main body. This creates a kind of artificial eclipse inside the camera. With the main glare gone, the much fainter light from the sun's outer atmosphere, the corona, becomes visible, and so do other faint objects like comets that happen to be flying past the sun. It's like trying to spot a tiny firefly flying next to a giant spotlight. You can only see the firefly if you block the spotlight. Our spacecraft are masters at doing this. This technology was absolutely essential because, from our perspective here on Earth, 3i Atlas was directly behind the sun during its outburst. If you tried to point a telescope on Earth at it, you would just be pointing at the sun itself. The sky would be too bright during the day, and at night the sun and 3i Atlas would both be below the horizon. There was no way to see it from the ground. Only our space-based coronagraphs could perform the magic trick of blocking the sun's light to reveal the faint traveller hiding next to it. We were completely reliant on our robotic eyes in space. Having 3 different spacecraft see the event was also critically important. Each one saw the event from a slightly different angle in space, or at slightly different times. This provides what scientists call triangulation. It helps confirm that the event was real and gives a more complete picture of what happened. Stereo A saw the initial brightening. SOHO's LASCO C3 confirmed the incredible rate of brightening over several days, and GO-19's instrument was particularly good at measuring the colour, providing the key evidence that the object was bluer than the sun. By combining the data from all 3, scientists can build a much more detailed and reliable story of what occurred. It's like having 3 witnesses to a car crash. One saw it from the side, one from the front, and one heard the sound. Together, their stories give you a full understanding of the event. The GO-19 satellite, our weather-watching friend, played a very special role. Its coronagraph was uniquely able to measure the sheer size of the glowing blue cloud. It was the data from GO-19 that led to the calculation that the cloud was an enormous 300,000 kilometers across. This was a critical piece of information that helped confirm the object was emitting its own light, rather than just reflecting it. A simple reflection wouldn't create such a vast, bright glow. So, a satellite designed to predict storms on Earth ended up giving us one of the most important clues in a major astronomical mystery. The way these instruments measured the colour is also clever. They have different filters they can use, like putting different coloured sunglasses in front of the camera. One filter lets in mostly blue light, and another lets in mostly red light. They take a picture with the blue filter, then a picture with the red filter. By comparing how bright the object is in each picture, they can calculate its true colour. They did this for 3i Atlas, and they also did it for the sun's light streaming around the coronagraph. The comparison was clear. In the blue filter image, 3i Atlas was exceptionally bright. This direct comparison is how they could say with confidence that this interstellar object was, for a few incredible days, bluer than the sun. The story of 3i Atlas is filled with numbers and measurements that can seem hard to understand. But at the heart of this mystery is one specific piece of math, a number so strange that it forced scientists to question everything they thought they knew about comets. This number describes the object's incredible brightening. To truly grasp why this event was so shocking, we need to look at this math and break it down into simple terms. We need to unpack the brightness measurements and understand the models that it completely broke. This is a story about the math that broke the models. In astronomy, scientists have a tool to describe how a comet's brightness changes. It's called a power law. That might sound complicated, but the idea is simple. It's a rule that connects how bright a comet is to its distance from the sun. As a comet gets closer, it gets brighter. The power law just tells us exactly how much brighter it gets for every step it takes closer to the sun. It's like a recipe. For a normal comet, the recipe says, for this much change in distance, add this much brightness. This is a predictable and reliable rule for almost every comet we've ever seen. For most comets, the number used in this power law, called the power law index, is around -3 to -5. Let's forget the minus part for a second and just think about the number. A bigger number means a more dramatic change in brightness. A comet with an index of 5 will brighten up much more quickly than a comet with an index of 3 as it approaches the sun. So, the range of 3 to 5 is the normal expected behaviour for a comet. It's the box that they all fit into. But 3i Atlas didn't fit in the box. Its power law index was measured to be -7.5. That number is staggering. It's far outside the range of normal comet behaviour. To put it into perspective, let's use a simple example. Imagine a comet with a normal index of -4. If you cut its distance to the sun in half, it might get about 16 times brighter. Now let's look at 3i Atlas with its index of -7.5. If you cut its distance to the sun in half, it would get more than 180 times brighter. That is a colossal difference. It's not just a little bit more active, it's a completely different kind of event. It's the difference between a candle and a searchlight. To get this number, scientists did something very straightforward. They took all the measurements of 3i Atlas's brightness from the spacecraft. They had data from before the object went behind the sun, and they had data from during its dramatic flare-up. They put all these data points on a graph. On one side of the graph was the comet's distance from the sun. On the other side was its measured brightness. For a normal comet, these dots would form a gentle curving line upwards. But when they plotted the data for 3i Atlas, they saw something amazing. As it got close to the sun, the line on the graph suddenly shot almost straight up. It was a visual representation of the brightness explosion. The steepness of that line is what gives you the power law index, and the line for 3i Atlas was incredibly steep. Now, science is all about being careful. The scientists who made these measurements know there can be errors. Measuring the brightness of a faint object next to the sun is very difficult. So they accounted for this. They calculated what they call the uncertainty. This is a range of possible values, not just one single number. So maybe the true number wasn't exactly -7.5. Maybe it was -6.5, or maybe it was even as high as -8.5. But here's the key point. even the lowest possible value in that range, -6.5, is still way outside the normal behavior for a comet. It's still a shocking and unexplained number. So even with the possibility of small errors, the conclusion is the same. 3i Atlas behaved in a way we have never seen before. Some people might ask, don't comets have outbursts all the time? It's true. Comets are unpredictable. Sometimes a pocket of ice under the surface can suddenly burst, causing the comet to flare up in brightness for a short time. This is a common and well-understood event. But what happened with 3i Atlas was different. A typical outburst is like a firework. It's a quick, bright flash, and then it fades away, usually over a few hours or a day. 3i Atlas was not a firework. Its extreme brightening was sustained. It maintained this incredible level of brightness for days. And it wasn't just seen by one instrument at one moment. It was tracked by multiple instruments on multiple spacecraft over a long period. This sustained power is not characteristic of a simple outburst. It points to a much more powerful and continuous process that was unleashed as it neared the Sun. It was more like a giant engine being turned on than a simple, brief explosion. This is why the math from 3i Atlas didn't just bend the models, it completely broke them. The brilliant blue colour of 3i Atlas is more than just a beautiful cosmic light show. It's a clue. It's a message written in the language of physics, telling us something profound about the nature of this mysterious object. To understand the message, we need to decode the meaning of that blue light. We need to explore the possible chemical processes that could create such a glow, and what they reveal about this visitor's secrets. Let's delve into why blue matters, and how we are trying to unlock the comet's secret code. First, we need to be very clear about what it means to be bluer than the Sun. The Sun produces light across the entire rainbow, but its output is strongest in the yellow part of the spectrum. An object that is bluer than the Sun is one that is giving off more light in the blue and violet parts of the spectrum compared to the yellow and red parts. Imagine you have two light bulbs. One is a standard warm yellow bulb, the other is a bright cool blue LED. 3i Atlas was acting like that blue LED, even though the only thing lighting it up was the yellow sun. This means it wasn't just reflecting, it was fundamentally changing the light or creating its own. Our space telescopes can measure this with great precision. As we mentioned, they use filters. A blue filter only lets blue light pass through to the camera's sensor. A red filter only lets red light through. The computers on the spacecraft take a picture through the blue filter and measure how many photons or particles of light hit the sensor. Then they do the same with the red filter. They then compare the blue light count to the red light count. For 3i Atlas, the number of blue photons was unusually high compared to the number of red photons, especially when compared to the sun's own light. This simple comparison is the hard evidence behind the claim that it was truly a blue object. So what could cause this blue glow? Scientists have a few main ideas, all pointing to some very interesting chemistry. One leading theory involves specific types of gas. When certain molecules are hit with energy from the sun, they get excited and then release that energy as light of a specific colour. Two molecules often found in comets are cyanogen, which is written as Cn, and diatomic carbon, written as C2. When these gases are present in a comet's coma, the glowing cloud around it, they often glow with a greenish colour. This is why many comets in pictures look green. But it's possible that under the extreme conditions near the sun, and with a chemical makeup we've never seen before, these or other gases could be made to glow a brilliant blue. Perhaps 3i Atlas contained a huge amount of a gas that we rarely see, one that glows blue when energized. Another idea has to do with dust. The dust coming off 3i Atlas might be very different from normal comet dust. We see an effect of this every day. Our sky on Earth is blue because of something called Rayleigh scattering. Tiny molecules of nitrogen and oxygen in our atmosphere are much better at scattering the blue light from the sun than the red light. So blue light gets scattered all over the sky, making it look blue. It's possible that the dust cloud around 3i Atlas was made of incredibly small, fine particles, maybe even smaller than the particles in smoke. These tiny dust grains could be extremely efficient at scattering blue sunlight, making the whole cloud appear blue. However, for this to explain the incredible brightness, the cloud would have to be extraordinarily dense with this special kind of dust. A third, and very exciting possibility, involves something called plasma processes. Plasma is often called the fourth state of matter after solid, liquid, and gas. It's a superheated gas where the electrons have been stripped away from the atoms, creating a sea of charged particles. The area around the Sun is filled with plasma, called the solar wind. When a comet passes through this, its own gases can also become ionized, turning into plasma. The interactions between these charged particles and the Sun's magnetic field can release huge amounts of energy as light. Think of a neon sign. A gas is trapped in a tube, and electricity energizes it, making it glow with a bright color. A similar thing could be happening with 3I Atlas, but on a cosmic scale, creating a massive glowing blue plasma cloud. There is one more clue that ties this all together. Months before 3I Atlas reached the Sun, astronomers had studied it from afar. They had already found something interesting about its chemical makeup. They detected a large amount of carbon dioxide, or CO2. In the cold of space, CO2 is an ice just like water, but CO2 ice is what we call a supervolatile ice. This means it turns into a gas at a much colder temperature than water ice. It's the same stuff as the dry ice that creates spooky fog for Halloween. Because it turns to gas so easily, it can cause very explosive activity on a comet. When 3I Atlas got close to the Sun, its large stores of CO2 ice could have vaporized all at once in a massive eruption. This violent release of CO2 gas could have been the engine that powered the whole event, creating the bright light and possibly the conditions needed for that specific blue glow. The mystery of the blue color is a direct window into the alien chemistry of this object from another star. With all these strange clues, the impossible brightness, the blue color, the sheer size of the glowing cloud, scientists are left with a massive puzzle. What could this object possibly be? The evidence doesn't fit neatly into any of our existing boxes, so the scientific community is now debating several big ideas. Each idea is an attempt to explain all the strange facts we've observed. Let's lay out these big questions and explore the three main possibilities that scientists are considering. What could 3I Atlas be? The first idea, and the one that many scientists believe is the most likely, is that 3I Atlas is a natural object. It's just a type of comet we have never encountered before. Let's call this idea number 1. It's a natural, super volatile comet from another star system. The thinking here is that comets that form around other stars might be made of very different stuff than the comets in our own solar system. Perhaps in the star system where 3I Atlas was born, there was an abundance of materials like frozen carbon dioxide, carbon monoxide, or nitrogen. These are the super volatile ices that turn to gas very easily. This interstellar comet could have been packed full of these explosive ices. As it travelled through our solar system and got close to our Sun for the first time, the sudden heat was a massive shock. It caused these ices to erupt with a force far greater than we see from our local, water ice-rich comets. This massive, violent outgassing could explain the huge brightening and create the conditions for the strange blue glow. It would be a 100% natural event, just a very extreme and rare one. The second idea is a little more complex. Let's call it idea number 2. It's a natural object, but it's undergoing exotic physical processes that we rarely get to see. This idea suggests that the basic object might be a comet or an asteroid, but its interaction with the Sun's intense environment created some truly weird physics. This could be things like the plasma processes we talked about, where the object's gases became super energized and glowed like a giant neon sign. Or maybe the dust it released had strange electrical properties that caused it to light up. This idea suggests that our models of how the Sun's energy affects objects are incomplete. 3I Atlas could be a natural laboratory, showing us new physical rules that we didn't know existed. The object itself might be normal, but the light show it produced was the result of a rare and powerful interaction that we just don't understand yet. The third idea is the most mind-bending of all. Let's call it idea number 3. It's something engineered. This is the hypothesis that 3I Atlas is not natural at all. It could be a piece of technology, or debris from technology, created by an alien civilization. In this scenario, the object could have been a probe designed to travel between stars. It might have been designed to use a star's energy to power up, recharge, or even send a signal. The intense heat and radiation from our Sun might have been the trigger that activated it. The blue glow wouldn't be from gas, it would be from power systems turning on. The extreme brightness could be an intentional signal, or just a byproduct of its technology. This is of course the least likely of the 3 ideas, Science always favours natural explanations until they're completely ruled out. But the behaviour of Three-Eye Atlas is so strange that this idea, as unlikely as it is, remains a possibility in the minds of some researchers. Each of these three ideas predicts different things that we should see when we look at Three-Eye Atlas again. If it's a super volatile comet, our telescopes should be able to detect the specific light signatures, or spectra, of the gases like carbon dioxide that are causing the glow. If it's an engineered object, we might see a shape that is not natural, like something sharp or symmetrical, or we might detect radio signals coming from it. Our upcoming observations are designed to look for exactly these kinds of clues to help us figure out which idea is correct. This situation is very similar to another mysterious interstellar visitor we had a few years ago, an object named Oumuamua. Oumuamua was strange because it was accelerating, moving away from the Sun faster than gravity alone could explain. Usually this is caused by gas jets from a comet, but Oumuamua had no visible gas or dust cloud. This puzzle led some scientists, like Avi Loeb from Harvard University, to suggest it could have been an engineered object, perhaps a thin, light sail. Three-Eye Atlas is our second big interstellar mystery. It doesn't have the same strange acceleration as Oumuamua, but it has its own unique and baffling puzzle with its light and colour. So the stage is set. When our most powerful telescopes, like the Hubble Space Telescope and the James Webb Space Telescope, turn their eyes towards Three-Eye Atlas in December, they will be on a mission. They will be looking for the specific clues that will help us solve this cosmic whodunit. Is it a strange natural comet, a display of unknown physics, or the first sign that we are not alone in the universe? The answers are waiting out there in the dark. The puzzle of Three-Eye Atlas is not just about its brightness and colour. Like any good mystery, it has other strange clues, other small details that don't quite add up. Before its main eruption of light, astronomers noticed other odd things about this visitor. These details, like a ghost-like tail and a slightly wobbly path, add new layers to the story and make the puzzle even harder to solve. Let's look at these other pieces of evidence, the ghost tail and the wobbly path. Long before Three-Eye Atlas got close to the Sun and put on its main show, when it was still far out in the solar system, astronomers noticed it had a tail. But this wasn't a normal comet tail which always points away from the Sun. This was something called an anti-tail. An anti-tail is a fascinating optical illusion. It happens when we on Earth are looking at a comet's orbit from a particular angle. A comet releases dust particles of different sizes. The smaller particles are pushed away from the Sun by solar radiation, forming the main tail, but larger, heavier dust particles are not pushed as much. They tend to stay behind in the comet's own orbital path. When Earth passes through the plane of the comet's orbit, our viewing angle makes it look like this trail of heavy dust is pointing towards the Sun, even though it's not. It's a trick of perspective. So, seeing an anti-tail itself isn't necessarily strange. But what was strange about Three-Eye Atlas was how its anti-tail behaved. It seemed to grow faster and be more prominent than scientists expected. This suggested that even when it was far from the Sun, the object was already releasing a significant amount of larger dust particles. This was an early hint that Three-Eye Atlas was more active than a typical comet at that distance. So, while the anti-tail itself was an illusion, the dust that created that illusion was very real, and it was a sign of unusual activity to come. It was the first whisper that this visitor was not what it seemed. The second, and perhaps more important puzzle, is found in the object's movement through space. Scientists can track the path of objects like comets with incredible precision. They use the laws of gravity, first figured out by Isaac Newton, to predict exactly where an object should be at any given time. For most objects, like asteroids, these predictions are perfect. Gravity is the only force acting on them, but comets are different. When a comet releases gas and dust, it acts like a tiny rocket engine. These jets of gas can push the comet around, causing it to stray slightly from the path that gravity alone would dictate. These tiny deviations from the predicted path are called non-gravitational forces, or orbital residuals. Essentially, it's a wobble in its path. Scientists did indeed see these tiny wobbles in the path of Three-Eye Atlas. This was not a surprise. Since they could see it was active and releasing dust to form the anti-tail, they expected to see it being pushed around a little by gas jets. But here is the central puzzle, a major contradiction in the evidence. The explosive brightening that we saw as it passed the Sun was a sign of a massive release of energy. An event that powerful should have been caused by gigantic jets of gas shooting out from the object. Those gigantic jets should have pushed the comet very hard, creating a very large and obvious wobble in its orbit. But that's not what the data showed. The wobbles in its path were very small. They were tiny, much smaller than you would expect from the incredible light show it produced. This is a huge problem for the simple comet explanation. How can an object produce a massive explosion of light, hundreds of times brighter than normal, without producing a massive rocket force that shoves it off course? It's like seeing a giant explosion but feeling only a tiny puff of wind. The cause and effect don't seem to match up. This contradiction has led scientists to wonder what was really going on. One possibility is that the brightening was not caused by jets of gas shooting out in one direction. Maybe the material came off the object evenly in all directions, like a sphere expanding. In that case, the forces would cancel each other out, and there would be no net push on the comet. This could happen, but it would require a very specific and unusual type of eruption. Another, more exotic idea is that the brightening wasn't caused by a huge amount of material being shot out at all. This ties back to the idea of light emission. What if the object was simply glowing? If the energy was released mostly as light rather than as moving gas and dust, then it wouldn't create a strong rocket force. This would neatly explain why it got so bright but didn't have a large wobble in its path. This observation, the small wobble, is a piece of evidence that could fit better with the more unusual ideas, like exotic plasma physics or even the engineered object hypothesis. An engineered object could, in theory, generate light without expelling mass, which would produce exactly what we saw, a huge increase in brightness, with very little effect on its trajectory. This subtle clue, hidden in the precise mathematics of its orbit, might be one of the most important pieces of the entire puzzle. Whenever a discovery as strange as this is announced, it's important to take a step back and ask a crucial question. Could the instruments be wrong? In science, this is not a sign of doubt, but a sign of strength. It's called skepticism, and it's the most important tool a scientist has. Before we can claim that we've found something new and revolutionary, we must first try to prove ourselves wrong. We have to consider all the ways our measurements could be flawed. Let's explore the world of the doubters and see why. Despite the risks of error, the observations of 3i Atlas are still being taken so seriously. Scientists who work with spacecraft and telescopes are experts at understanding what can go wrong. They know their instruments are not perfect. A coronagraph, the tool that lets us see faint things near the sun, is an amazing piece of technology, but it has its challenges. One major problem is something called stray light. The sun is so incredibly bright that even when you block it with a disk, some of its light can bounce around inside the telescope and hit the detector. This stray light can create false bright spots or make the entire image a little bit brighter, which could fool you into thinking an object is brighter than it really is. Scientists have to be very careful to subtract this stray light from their images. Another problem that affects space telescopes is cosmic rays. Space is filled with tiny, high-energy particles that are constantly zipping around. If one of these cosmic rays hits the camera's detector, it creates a bright spot in the image that looks just like a star. Scientists have to use clever software to find and remove these cosmic ray hits, so they don't mistake them for real objects or real changes in brightness. If a lot of cosmic rays hit the detector near where 3i Atlas was, it could have potentially made it look brighter. There's also an issue called saturation. A digital camera sensor is made of tiny pixels, and each pixel can only count up to a certain number of photons or particles of light. If an object is too bright, the pixel gets overwhelmed and just reports its maximum possible value. This is called saturation. It's like trying to measure the water from a fire hose with a tiny teacup. The cup just overflows, and you don't know how much water you're really dealing with. If the images of 3i Atlas were saturated, it would make it very hard to measure its true brightness. Scientists would know it's very bright, but they wouldn't know exactly how bright. This could make calculating that power law index of -7.5 very tricky. Because of all these potential problems, scientists have developed many ways to check for and fix these errors. They have complex computer programs that model the stray light inside the telescope so they can remove it. They take multiple pictures and compare them to identify and eliminate the random cosmic ray hits. They design their cameras with special modes to handle very bright objects without saturating. They also do things like taking dark frames, which are pictures taken with the camera's shutter closed. to measure the electronic noise in the detector itself, which they can then subtract from the real images. It is a long and careful process of cleaning the data before they can even begin to do the science. So, could all of these strange observations of 3i Atlas just be a result of one of these errors? Could it be a big mistake? It's possible, but it is extremely unlikely. And the reason for this comes down to one powerful fact. The most important thing to remember is that 3 different spacecraft, built by different teams, operated by different agencies, all saw the same strange brightening and the same blue colour. Stereo A, SOHO and GO19 are completely independent systems. For this to be an error, it would require a huge and unbelievable coincidence. An instrument problem would have to happen on all 3 spacecraft at the same time in the exact same way to create the illusion of this event. The chances of that happening are incredibly small. The fact that we have independent confirmation from 3 separate sources is the strongest evidence we have. It turns the observation from a maybe into a very likely. It would be like if 3 people who have never met each other all came to the police and described the exact same, very strange-looking getaway car leaving the scene of a crime. It would be very hard to argue that they all just imagined it. This is why, despite the healthy skepticism and the careful checks for errors, the scientific community is taking the mystery of 3i Atlas very seriously. The evidence is simply too strong to dismiss as a simple glitch. The past is a puzzle, but the future is a countdown. All of this data, all these strange clues, have led us to this moment. The scientific community, and indeed the world, is now looking ahead to a specific date on the calendar. The story of 3i Atlas is about to enter its next and perhaps most exciting chapter. We are now on a countdown to discovery. Let's look at what happens next and what scientists are hoping to learn when this mysterious visitor reappears from behind the sun. The key date is December 19th. On this day, 3i Atlas will reach a point in its orbit where it is closest to Earth. More importantly, it will have moved far enough away from the sun in our sky that it will no longer be hidden in the sun's glare. It will be fully visible again to our powerful ground-based telescopes and our most advanced space observatories, like Hubble and the James Webb Space Telescope. After months of analysing the strange data from its solar flyby, scientists will finally get a new, clear look at the object. Everything we have discussed so far is based on what happened in October. What happens in December could change everything. There are 2 main possibilities for what we might see, 2 different scenarios that could unfold. Scenario 1 is the most exciting. In this scenario, 3i Atlas stays super bright. This would mean that the strange process that was triggered by the sun is still going on, even as it moves away into colder space. If it stays this bright, it might even become visible to amateur astronomers with good binoculars or small telescopes. Imagine being able to go into your backyard and see this mysterious interstellar object glowing with your own eyes. This would be an incredible opportunity for both scientists and the public. A continuously bright object would allow for long, detailed studies to figure out what is causing the light. Scenario 2 is also very possible, and perhaps more likely based on normal comet behaviour. In this scenario, 3i Atlas fades quickly. Many comets experience outbursts near the sun, and then as they move away, they dim back down to their normal faint selves. If this happens, it would be a bit disappointing for stargazers. It would leave us with a ghost. We would have the incredible data from its flyby, but the object itself would be too faint to study in great detail. We would be left with more questions than answers, and the mystery might remain unsolved for a very long time. What we see in December will tell us which of these paths the story will take. Regardless of whether it is bright or faint, scientists will be ready with their best tools. They will use a technique called spectroscopy. This is where they take the light from the object and split it into its rainbow of component colours. Inside this rainbow, there will be bright or dark lines, like a barcode. This barcode can tell scientists exactly what gases are in the object's glowing cloud. They can look for the signature of carbon dioxide or cyanogen, or other, more exotic molecules. Spectroscopy is the key to unlocking the chemical secrets of 3i Atlas, and could prove or disprove the super volatile comet idea. They will also use another tool called polarimetry. This is a technique that studies the way light waves are aligned. When sunlight bounces off dust particles, the light becomes polarized. By studying the polarization of the light from 3i Atlas, scientists can learn a lot about the size, shape, and composition of the dust particles it is releasing. This could tell us if the dust is made of normal, fluffy comet material, or something much stranger that could explain the blue colour, and of course, they will take pictures. High-resolution cameras on Hubble and James, Webb will try to get the sharpest possible images of the object. They will be looking for any signs that the object is breaking apart. Sometimes, extreme activity can cause a comet's nucleus to shatter into smaller pieces. They will also be looking for strange shapes. Is the object at the centre of the glow a simple, potato-shaped rock, or does it have a more unusual, non-natural structure? A clear image, even of a tiny dot, could provide a wealth of information. This is a global effort. While the big professional observatories will be leading the charge, amateur astronomers around the world can also play a vital role. If 3i Atlas does stay bright, the global network of amateur observers can help track its brightness night after night. This constant monitoring is something that professional telescopes, which have busy schedules, often can't do. The countdown to December 19th is on. The telescopes are being prepared, the observation plans are being made, and a world of curious minds is waiting to see what this interstellar traveller will show us next. The mystery of 3i Atlas is more than just a single, strange event. Its discovery has sent ripples through the scientific community, forcing us to ask bigger questions about our place in the universe. This single object, a tiny speck of dust from another star, has the potential to change our understanding of comets, of space exploration, and of the cosmos itself. It is a moment that could lead to rewriting the textbooks. Let's explore the broader implications of this mystery and what it means for the future of science. First, 3i Atlas forces scientists to rethink how they classify objects from other star systems. For a long time, we've had two simple boxes: asteroid, which is a dead rock, and comet, which is an icy body that becomes active near the Sun. The first interstellar visitor, Oumuamua, didn't fit either box well. It had no visible comet-like activity but was still accelerating. Now, 3i Atlas comes along, and it also breaks the mould. It is fantastically active, more active than any comet we've ever seen, and it has a strange colour and a mismatch between its brightness and its orbital wobble. It seems that visitors from other star systems are not going to fit neatly into the categories we've created based on our local objects. We may need to create a whole new classification system for these interstellar travellers, acknowledging that they can be much more diverse and strange than we ever imagined. This event also highlights the need for a new kind of space mission. Right now, we are mostly passive observers. We wait for things to happen in the universe, and we watch them from afar with our telescopes. But when a sudden, rare, and important event like the brightening of 3i Atlas occurs, we are left wishing we could have been there up close. This points to the need for faster, more flexible space missions. We need the ability to react quickly to surprising discoveries. Imagine if we had a small fast probe ready to launch, one that we could have sent on a trajectory to fly by 3i Atlas as it was flaring up. The data we could have gathered would have been incredible. This mystery shows us that our current approach to space exploration, with missions that take decades to plan, might be too slow for a universe that is full of surprises. On a more detailed level, scientists will now need to update their computer models of comet chemistry. For decades, these models have been based on the comets in our own solar system, which are mostly rich in water ice. The idea of super volatile ices like carbon dioxide playing a dominant role was known, but 3i Atlas suggests that their effects can be far more extreme than previously thought. Scientists will need to build new models that include these weird materials and other strange chemistries that might exist in objects from other stars. They will need to figure out what combination of materials and physical processes could possibly recreate the light show of 3i Atlas in their computer simulations. This will lead to a much deeper understanding of how these objects work across the galaxy. The way we observe this event also gives us ideas for the future. We saw it because we had a few coronagraphs in the right place at the right time, but what if we had more? Some scientists are now proposing the idea of coronagraph networks. This would be a system of many small cheap satellites in space, each with a coronagraph, constantly watching the Sun from all angles. This network would act as a 24/7 surveillance system, ensuring that we never miss another unexpected event happening near the Sun. It would be a true early warning system for strange visitors and other solar phenomena. Finally, the mystery of 3i Atlas teaches us something about how science is shared with the public. It is a story that has the potential for incredible hype, especially with the small but real possibility of it being alien technology. It is important for scientists and science communicators to share the excitement of this discovery responsibly. We need to be clear about what we know, what we don't know, and what are the different levels of possibility. We must balance the thrill of the unknown with the need for careful, evidence-based thinking. This mystery is a perfect opportunity to show the world how the process of science really works, with curiosity, careful measurement, open debate, and a willingness to be completely surprised. Ultimately, 3i Atlas is a profound reminder. It reminds us that the universe is not a solved problem. It is far stranger, more complex, and more wonderful than we often imagine. And it is inviting us to keep exploring, to keep questioning, and to be ready for the next surprise. The frustrating thing about a mystery like 3i Atlas is that we are so far away. We are like detectives trying to solve a crime by looking at blurry security camera footage from across the street. To really know what's going on, we need to get up close. We need to send a detective to the scene. This is why the discoveries of Oumuamua and 3i Atlas have energized a new field of space exploration, designing missions to catch the next visitor. Let's look at these exciting future mission concepts, like interceptor probes, designed to chase down and study these interstellar objects directly. The big idea that is gaining momentum in the space agencies of the world is for a rapid response interceptor probe. The concept is simple but brilliant. We would build one or more small, fast spacecraft and then put them in a parked orbit in space, waiting. They would be kept ready to launch at a moment's notice. Then, when our sky surveys and AI systems detect a new interstellar object entering our solar system, we would quickly calculate its trajectory. Mission Control would then fire up the interceptor probe, sending it on a high-speed path to meet the object. It would be a robotic chase through the solar system. These probes would be packed with scientific instruments. They would fly right up to the object, getting much closer than we ever could from Earth. They would have high-resolution cameras to take detailed pictures of its surface, looking for strange shapes or features. They would have instruments called spectrometers to sniff the gases coming off the object, telling us exactly what it's made of. They could even carry a small impactor to kick up a bit of dust from the surface, allowing another instrument to measure its composition directly. A mission like this would solve the mystery once and for all. We would know if it's a rocky asteroid, a gassy comet, or something else entirely. This isn't just a science fiction dream. This kind of technology is real, and missions are already being planned. The European Space Agency, ESA, is already building a mission called Comet Interceptor. Its goal is to do exactly this, but for a comet from our own solar system. It will launch and wait in space until a suitable long-period comet is found, one that we haven't seen before, then it will be sent to fly by it. Comet Interceptor proves that the technology and the concept are ready. The challenge is adapting this idea for the unique demands of an interstellar object. Interstellar visitors are often moving much faster and give us less warning time, so our interceptor probes would need to be even faster and more agile. The main challenges are not technological, but practical. The biggest hurdle is funding. These missions cost money, and it can be hard to get governments to approve funding for a mission that might have to wait in space for years before it is used. The other challenge is launch readiness. We would need to have powerful rockets on standby ready to launch our interceptor on very short notice. This is a very different way of doing space missions, which usually have launch dates set many years in advance. It requires a new way of thinking, more like a fire department that is always ready to respond to an emergency call. But imagine the payoff. Picture a future mission control room, years from now. A new interstellar object has been detected. The interceptor probe has been launched and has been travelling for months. The day of the flyby arrives. The team is gathered watching the screens as the first data starts to stream back from deep space. The first close-up images of an object from another star system appear on the main screen. For the first time, humanity would see what these visitors truly look like. Is it a lumpy, dark-coloured rock covered in exotic ices? Is it a sleek metallic object with sharp angles? The secrets of Oumuamua and 3i Atlas would finally be revealed. Missions like these would remove all doubt and speculation. We wouldn't have to guess based on faint glimmers of light seen from a billion miles away. We would have definitive, close-up data. We would have the answers. These interceptor missions represent the next great leap in our exploration of the cosmos. They would change us from being passive stargazers into active explorers of the galactic neighbourhood. And the strange behaviour of 3i Atlas is the perfect reason why these missions are not just a good idea, but an absolute necessity if we are serious about understanding the universe and our place within it. Finding a single, strange object like 3i Atlas in the vastness of the sky is like trying to find a specific grain of sand on all the beaches of the world. It's an impossible task for a human, but for a machine, it's just another day at the office. The unsung hero in the discovery of cosmic anomalies is artificial intelligence. AI is our tireless eye in the digital sky, and its role in finding and understanding objects like 3i Atlas is absolutely critical. Every single night, all around the world, robotic telescopes scan the heavens. They take millions of high-resolution images of the stars. This creates a flood of data so massive that no team of humans could ever hope to look through it all. This is where artificial intelligence comes in. Powerful AI programs are designed to do one thing: look for change. They take a new image of a patch of sky and compare it to an older image of the same spot. They are programmed to spot anything that is new, anything that has moved, or anything that has changed in brightness. Projects like the Zwicky Transient Facility, or ZTF, in California are masters of this. Their AI systems are responsible for discovering thousands of new cosmic events every single night. The AI automatically flags things like supernovas, the explosion of distant stars. It finds asteroids that are moving across the sky, and it spots strange, flickering stars that might be clues to new types of physics. The AI acts as a filter, sorting through the billions of uninteresting static stars to find the few dozen that are doing something new and exciting. It then sends an alert to human astronomers, telling them, hey, you should point a bigger telescope at this spot right here. Humans are good at deep thinking and understanding context, but we are slow and we get tired. AI is the opposite. It is incredibly fast and it never gets tired. It can perform billions of calculations per second, 24 hours a day, without ever making a mistake. It is this partnership between the brute force capability of AI and the clever intuition of human scientists that makes modern astronomy possible. We simply could not do it without our AI partners. In the specific case of 3i Atlas, AI almost certainly played a key role. When the data from the solar telescope started coming down, an AI program would have been analysing it. This AI would have been trained on what normal comets look like. It would know the expected brightness curves, the usual power law indexes. When it saw the data from 3i Atlas, with its brightness shooting up at a rate of -7.5, the AI would have immediately flagged it as a major anomaly. It would have recognised that this pattern of behaviour did not match anything in its database of known comet types. It would have sent an urgent alert to the science team, effectively shouting, "This one is weird, look at this." This allows scientists to focus their attention on the most interesting events, rather than wasting time on the normal ones. AI also helps in another crucial way. It helps us see more clearly. The images that come down from space are not perfect. They are filled with electronic noise, stray light, and cosmic ray hits. AI algorithms are now being used to clean up these images. They are incredibly good at learning what is a real signal and what is just noise. An AI can look at a messy image and, based on its training, remove all the unwanted artifacts, leaving behind a much clearer picture of the faint object we want to study. For something like 3i Atlas, AI-powered image processing could have been what made the faint, 300,000 kilometre wide blue glow stand out clearly from the noisy background near the sun. Looking to the future, the role of AI in this search will become even more important. Some scientists are now training AI to look for things that don't look natural at all. They are teaching AI to search for technosignatures. These would be signs of technology from other civilizations. An AI could be trained to look for patterns that don't match our known laws of physics. For example, it could look for an object that moves in a way that isn't a smooth orbit, or an object that emits a signal that is clearly artificial and not just random cosmic noise. In the future, it might not be a human who makes the first contact. It might be an AI, tirelessly sifting through the digital sky, that first spots a signal from the stars and tells us that we are not alone. We have travelled through a story of impossible brightness, strange blue light, and deep cosmic questions. We have looked at the evidence, considered the possibilities, and wrestled with the unknowns. Now, as we approach the moment of new discoveries, we are left with the final unanswered questions. Where do we stand now? And what does this all mean for our future as we look to the stars? Let's bring together all the threads and look at what the cosmic future may hold. Based on everything we know so far, most scientists still believe that the most probable explanation for 3I Atlas is a natural one. They would say there is about a 60% chance that it is an extremely exotic comet, one loaded with unusual super volatile chemistry that we've never seen before. This explanation fits many of the facts and doesn't require us to invent any new physics or believe in aliens. It simply requires us to accept that the universe is a diverse place and that comets from other stars can be very different from our own. It is the simplest and most elegant explanation, and science always prefers the simplest answer. Then there is the possibility that we have made a mistake. There is a chance that the strange behavior is not real, but is instead the result of instrument errors or problems with how the data was analyzed. This is the cautious, skeptical view. Scientists would place this possibility at around a 30% chance. Given that 3 separate spacecraft saw the event, a simple error is very unlikely. However, it's possible that there is a more subtle flaw in our understanding of how these coronagraphs work when an object gets this bright, this close to the Sun. It's an outside chance, but one that must be considered until it is definitively ruled out by the new observations. And finally, we have the least likely but most exciting idea. This is the hypothesis that 3I Atlas is engineered, a piece of alien technology. Scientists would probably put this chance at 10% or even lower. It is a long shot, but it is not zero. The fact that the object's behavior is so hard to explain with natural means is what keeps this small possibility alive. It is the what-if that drives our curiosity and our search for answers. This is the idea that captures the public imagination and reminds us of the profound stakes involved in exploring the universe. It is very important to remember that these percentages are not facts. They're just a way of expressing our current level of confidence in the different ideas. They're a snapshot of the scientific debate as it stands today. These numbers will change. As we get new data from the upcoming observations in December and into early 2026, we will be able to test these ideas. If we find the spectral signature of carbon dioxide, the chance of it being a natural comet will go way up. If we see a distinctly unnatural shape, the chance of it being engineered will skyrocket. The science is not finished, it is just beginning. As we wait for these scientific results, we encourage everyone to participate in the journey of discovery. You can safely observe the sky. Check trusted astronomy websites for information on where to find 3I Atlas in the night sky. If it does stay bright, it might be visible with a good pair of binoculars or a small telescope. Being a part of that act of looking up connects us all to this grand cosmic mystery. It connects us to the generations of humans who have looked at the stars and wondered, what's out there? Ultimately, 3I Atlas is a gift. It is a gift of wonder. It challenges our understanding of the universe and reminds us that there are still great discoveries to be made. It invites us to be curious, to ask big questions, and to keep exploring. No matter what the final answer turns out to be, a strange comet, a glitch in the data, or a visitor from another world, the journey to find that answer will make us smarter, more capable, and more connected to the cosmos. Whether it's a super comet, a trick of the light, or something truly alien, 3I Atlas is forcing us to rethink the universe. Keep looking up, stay curious, and let's discover what's next together.